So, so the lecture today is going to be about path integrals and their use in quantum field theory. So I'm going to start by reminding you how path integrals work in quantum mechanics. Okay. So suppose we have this is elementary stuff. Most of you know it. We're just going to do this. That's a segmentation. Okay. So suppose we had a quantum system with an Hamiltonian which was d squared by 2m. That's v of x. The canonical first quantum mechanical system anyone studies. Okay? It's the quantum mechanics of a particle moving in one dimension with canonical kinetic term and some potential. Okay. Now, as all of you know, the evolution operator in quantum mechanics is e to the power minus I h bar h times t. Okay? This is something called u of t. And it's the operator that takes a state at time t1 to a state at time t1 plus t. Okay? So suppose you know your state is psi at t1, and you want to know what is the state psi. What is psi at t2? The answer to that question, as all of you know, is e to the power minus I. Solve the Schrödinger equation h of t2 minus t1. This evolution operator is clearly a useful thing in quantum mechanics. It's the operator that allows you to translate things in time. It's the operator that allows you to ask the basic question of all physics, that is given a state at any time.
Without the t, right?
Thank you. Given a state at any time, what is the state at a future? Okay. Now, as all of you know, over what is it, 70 years ago now, Feynman came up with a very nice path integral representation of this evolution operator, which we will now discuss. Okay, so this is an operator. The operator has two indices. We're going to try to represent it by number. The only way we can do that is look at matrix elements. So let's suppose we are interested in the matrix elements of the operator e to the power minus I h t, starting at x1 and ending at x2. Okay. Now, the basic idea, the key idea, the key point was this. So this is the operation that we will sometimes, in words say is the amplitude for propagation of the particle from x1 at time, let's say 0, to x2 at time t. Of course, I could have equally said x1 at time t1 and x2 at time t1 plus t. So this translation in minutes, time translation in minutes as well. Now the key observation here is that this operator can be built out of breaking it up into operators for evolution over smaller times. And the key identity is the completeness of states of quantum mechanics. This is true always. This is just a true statement of decomposition of the identity at a basis. Okay, so at any point of time we could rewrite this operator as e to the power minus I h, let's say t1, t minus t1. Times e to the power minus I h t1 times x1. This is trivial. I've used the fact that these two operators commute because h is the same h. Okay. And then I can insert this identity into here. Okay. Now, once I insert that identity into here, so let's call this object g of x1 to x2 in time t. Clearly, what we get is the identity that g of x1 to x2 in times t, by inserting this our identity, is equal to the integral of g of x1 to x in time t1 times g of x to x2 in time t minus 2. this clear to everyone? Okay? So, this evolution operator obeys this property that if you know it for smaller times, you can build it up for bigger times by compounding and integrating. Okay? So then, finally observe that since this was the case, we could try to repeat this procedure many times and build it up out of compounding infinitesimal time evolutions. Okay? So, what's the idea? Let's suppose we call this. Okay. So suppose we define various time steps. So let's say that for simplicity this is at time 0 notation. So we have x1 at time 0. Now we break this up into many small time steps. Let's call the first time step. Okay, I should have called this T1 because in conflict with my notation. Let me call it U. This is U. Okay, let's call the first time step T1. That T1, let's say that this, and let me also put this X, initial and X minor. Sorry. So suppose it's an x0 at time t0, which is 0. And we'll call this x1 at time t1, x2 at time t2, up to xf, xn at time tn, x1, xf at time tn, which is equal to t. Okay? So what we're going to do is break up this evolution operator into, and we will use the notation that delta t1 is delta tn m is equal to tm minus 1. What we're doing is breaking up this entire interval from 0 to t into n different subparts. Okay? So the first subpart is at t1, the second subpart is at t2. It's between 0 and t1, the second one is t1 to t2. Up to t n minus 1 to t. Okay? So then we take this evolution operator, break it up into those products of those various evolution operators, and between each of them insert the complete set of states that we discussed. Okay?
Don't get integral imply integral also over t, because you are like breaking the integral into.
We're breaking the integral, but it's going to be a product. So let's write.
One term will cancel the other. Delta t different.
No, let's write the formula. So the formula is that g of x initial to x final in times t. So what is it? So now we will have a product over all intermediate times. So m is equal to 1 to n minus 1. Okay. G of now x n minus 1 to xn in time tn minus what we call delta. Okay, and then here xf, xi, xf, integral with the dx n. Okay, so I've got n minus 1 guys, and what have I missed here? I've taken this from 0 to 1, and then if this is only up to n minus 1, sorry, this is m. Let me write this list fancily. dx1, dx2 up to dx n minus 1, and then these these g's, there is a product that is equal. Okay? So what we have is a product of n factors of evolution, because we've broken up the time interval into n little subintervals. But because we've broken up n little subintervals, there are n minus 1 intermediate positions. And we have to integrate over those intermediate positions. Okay, this is an obvious idea. And Feynman's main insight, following up by an observation by Dirac, was that when this thing is infinitesimal, I mean, each of these infinitesimal guys are rather easy to compute. So let's go ahead and compute. Okay. So what we want to do is to compute this evolution operator. We want to compute, let's say, b e to the power minus I h delta t, and then when delta t is now some infinitesimal object, we want to work to first order n. Okay? And the other way to do this computation goes as follows. The first thing to do, I rubbed out this h, but you remember it's p squared by 2m plus b of x. And the first thing to do is to remember that in general, you cannot, it's not true that e to the power p squared by 2m plus b of x in general times some t is not equal to e to the power minus I times p squared by 2m t times e to the power minus I times b of x. See, this is not true. The reason is that p squared and b of x is commute. Okay? However, and this is what makes the finite evolution difficult to evaluate at much in the non-commuting nature of various operators. Okay, however, if this t was an infinitesimal, the lack of commutation is expressed by the Campbell-Baker-House law of identity. And involves the commutator of this operator, p squared by 2x times t, with v of x times t, the first correction. It involves that. And that's about a t squared. Okay? So, if we're only keeping terms to order delta t, we can ignore the fact that these two operators will commute. Okay? So you can write it as a product of two different operators. So that's what we're going to do. We're going to write this as follows, and you can write it in any order. The difference again is proportional to commutator, so delta t squared. So let's write this as b e to the power minus I v of x times delta t h cross e to the power minus I by h cross p squared by 2m. Valid to first order infinity. Okay? Now the next step is to say, well, this is really easy. Because, as you know, it's a property of any function of the operator x acting on an eigenstate of x. You just replace that function by the value of the x. Okay? So this is equal to v to the power minus I by h cross v of b delta t times b e to the power minus I by h cross b squared by 2m delta t. That's it. Okay? And now, b is a bit irritating to compute in the position basis. It's easier to compute it in a momentum basis. So let's insert a complete set of states, but using the momentum basis. So this is b e to the power minus I by h cross b squared by 2m delta t p a integral dp times this. Okay? Now that we move to the momentum basis, this is trivial to compute, because here we just act as operator p and we replace it by number p. So that is equal to e to the power minus I p squared delta t by h cross 2h cross m, I'm forgetting the 2 separate, times Now, what's this? Inner product of B with B. And inner product of B with A. So this is equal to e to the power I h bar P of A minus B. Because the inner product of B with A is e to the power h bar B times A. Sorry, e to the power I h bar P A. This is the wave function. This just represents. I did it wrong. This is something. This is just the wave function of the momentum eigenstate in position basis. E to the power h bar B, and this is the complex. Okay? So, what have we finally concluded? We finally concluded that we have e to the power minus I p squared delta t by 2h bar m times I plus I h bar p into b minus a. H bar should be in the denominator. Okay, here. Thank you. Thank you. Okay, great. We're still supposed to do an integral over p. Okay, so even before doing the integral over p, let's note that this thing here can be written in a pretty nice form. Suppose we divide and multiply by delta t. And we forgot to carry this e to the power I v b of b by h plus. Yeah, let's carry it. So this minus I v b by h bar delta t. Okay, and now this can be written in a pretty suggestive form. This is simply equal to e to the power I, or e to the power minus I. It's e to the power I times p x dot by h bar minus h of p and b times delta t. But by x dot by definition is simply b minus a. Okay. Now the reason I've written on this form is that it might remind you the whole thing is by h. So this quantity reminds you of something. As you know from your study of classical mechanics, that quantity, if we use canonical definition, if we use Legendre transform to substitute for p in terms of x, this quantity is simply the action. Okay? Now, it's a fact of life. Actually, there's a more general thing to say, but I won't say it at the moment. But it's a fact of life that a quadratic path integral. Okay, so what's a Legendre transform? The Legendre transform asks you to solve for p. Okay? By thinking of this as a function of both p and x, writing down the equation of motion for p, and plugging in the solution of that equation of motion. Okay? The series of steps has this fancy name, Legendre transform. Okay. Imagine that it's actually a function of both x and p. Use the equation of motion for p. That gives you an equation. The equation will be x dot is equal to del h by del p. Use the equation of motion, solve for p, plug that back in, and you get a function just of x. Okay? So, but that's the thing that will give you the action. But it's a fact of life about quadratic integrals, quadratic in the exponential, Gaussian integrals, that up to a determining factor, they implement that procedure. Do you know what I mean? So, what I'm saying is now, in our particular case, our h was quadratic in p. Okay? So if you just did the Gaussian integral, okay? The answer to that involves a measure factor, a determinant of this h bar m by delta t. In this case, the determinant is just determinant of a number. So 1 over square root of h bar m. Okay, it is equal to square root of h bar m by delta t. Okay, that's some pi business coming from e to the power minus some numbers. Okay, times just solving for the equation of motion for p and plugging that back in. Is this familiar to you? Okay, so I won't bother to evaluate the Gaussian integral. I just use the fact that I know what the answer will be up to a normalization, which we will probably never need in this course. We'll be doing it once. So I'm going to ignore normalization.
Why is B appearing here rather than I have no appearance of A here?
Why is B appearing here? You see, that's because I broke symmetry by inserting the complete set of states here rather than here. Okay? And we have to remember that all of these expressions are approximate. That is, they're valid only to first order and delta t. Okay? So to this first order and delta t, as we will soon see, B and A will always be forced to be infinitesimally nearby. Okay? So it won't make a difference. You see, what we're going to do is to get what we're doing is breaking up this path integral into steps. And whether you use the potential here or the potential here when the steps are taken to be very small, doesn't really make a difference. Because it's all going to be the parts in which these steps are finitely separated will contribute negatively. Surprise.
So for higher orders, this won't be valid, right?
Higher orders in delta t.
Delta T,
This won't be valid. But you see, we never need higher orders in delta t. What we're doing is like it's like an integral. Well, if you think about how you sum an area on that curve, you got this, and you say, well, what's the answer? It's the height here times this distance. Now you could ask, no, why not the height here times this distance? And you're right, this is an approximation. Say the height here times this distance, or the height here times this distance. They're all approximations. Okay? But the point is that the error you make scales like delta t squared or delta x squared. Okay? And you're going to take the limit delta x goes to 0. So it doesn't matter. It's the same kind of thing that's going to happen. Okay? There's an error if delta t was finite. But in the limit that we'll be interested in, we don't care about those errors. Okay, see? The usual thing. Okay, great. So now just substitute, just using what we know, what we will get is that this is simply e to the power I by h times the action, which it was simply the action we started with, which was x dot m x dot squared by 2. X dot, remember, is code for b minus a. B minus a by delta t. Okay? Minus v of b, the whole thing. Okay, at this point, this one times a constant normalization factor, which will be of no importance to much of what I will say. Is this clear? Okay, so we've got and now we take this formula together with the formula we derived earlier in this lecture about how you take the evolution operator and decompose it up into a product. And we remember that the product of exponentials is the sum upstairs. Okay? So we have derived the formula that g of xi to xf in times t is equal to path integral e to the power I by h cross s dt mx dot squared by 2 minus v of x. And in this derivation we also have precise meanings for this dx and this action. What does this dx mean? This dx just means this dx is just product, because it came from the product formula. dx1 to dxn minus 1.
So the VF is a different times commute over.
Sorry?
The VF is a different times commute over.
No, now every was dealt with here. Now we're looking at a matrix element. Matrix element is a number, and now we just process numbers as numbers are processed. Okay? Okay. Now what does this mean? This is product of this times the factors that we got by doing this integral here. I'm not keeping track of that. Okay? So times the normalization. But you can easily keep track of it if you want. You see, right? It's just some pi's and factors of I and square root of h by m by 10 these. Okay? That's what this dx means. What does this action mean? This action just means the action for each interval added up. It's just this object added up over an interval. Okay? Just one last statement. We've got n intervals, but n minus 1 integration variables. The two end points supply the data need to complete evaluation of the action.
So, while writing the argument of exponential, you're taking the limit of everything tends to 0, right?
Right.
But your normalization factor will go. Right?
Will go.
So, formally, how do you go around that?
How do you go around that? You see, as you will see, what people always be interested in is ratios in which the normalization will get.
Yes.
Okay? However, this is a clip answer because it's not totally satisfying. Often in physics, you don't feel totally satisfied unless you can control it, and that's a good instinct. Now, yeah, there's a better answer to the question. Maybe I'll pick that as one of the first assignment. I'll ask you guys to work it out. Okay. The better answer is that if you want to account for this normalization, okay, you can do it by starting with a renormalization. You know, it's often said that in quantum mechanics there's no renormalization. And that's true for everything non-trivial. But there is a sense in which the action you have to use here is not quite the classical action, but includes what's called a counter term. And the inclusion of this counter term cancels this infinite factor. I won't try to explain it here, but I'll give you an assignment in your first problem. Okay. Actually, Polchinski may work this. I think he works this. So, the canonical way to answer this question is to just work out the path integral for the harmonic oscillator. Okay? And to work it out including these extra terms. Okay, so two answers. The first one is that we never need really to answer your question. Okay? The second one is we can, but I won't take the time. Okay.
Maybe you would work out with the same partial if your Hamiltonian interval time dependent.
A good, very good question. Yes, nothing I said here would have changed v of x was a function of v of x over t. Nothing. Okay? Except that we would have to be careful in the notation. It wouldn't be the product of the same operator all the time. You know what we would. You might be worried here. You might be worried by saying that look, you started off saying that you could break this up because the operators commute, and then if v of x is a function of v, and they no longer commute. I mean, you see that is a red here, because what is the right evolution operator? You have to start with the right object. What is the right evolution operator in quantum mechanics when v is a function of time? So tell me. Path order, trimodal, right? Exactly. It can be formally written as this object. Path order e to the power minus I h of t. Okay. Now this is a formal object. It's everything. Okay. This is a formal object. It's a p here is very important. What does it mean? What it means is exactly what we're doing in the part. That is, break up this evolution operator into evolutions over little time steps and multiply the corresponding operators. You see, where does that come from? It comes from the fact that over any infinitesimal time, no operator is time dependent. Okay? So, the general principle by inserting complete set of states works even for time dependence. So the general formula that you can break it up into infinitesimal evolutions doesn't care about time. Okay? And the object that the object that we wanted was this path ordered object, which was the product of the infinitesimal evolution operators by definition. So that's the object we started. And then, just between these infinitesimal operators, we insert complete set of states. Everything. No difference. Yes.
Going back to this thing, you said that you cancel the infinity in the n by adding counter terms and all that.
Right.
But that should be wrong, right? Because I would assume that the infinity in the n cancels the fact that you have infinite integrations going on.
We have infinite integrations. But
If you cancel the infinity in the n, you'd have an infinity in a numerator and that would be good.
If you take it as a limiting process, so you'll have two factors which come out and cancel out.
Yeah.
Then the limit is probably
Yeah. No, but what you're saying is correct. What you're saying is correct. You see, there are basically two ways of doing this. Of course, see. No, actually, what you're saying is correct. See, if you just do exactly what I did, okay? If you just do exactly what I did, then I started with a well-defined object. So I'll end up with a well-defined object. And the infinities will cancel for the reason that you said. Okay. But, okay. So you're right that I will draw my statement. Sorry, that was wrong what I said. Now let me tell you what I meant to say. Okay. What I meant to say was the following. In order to keep track of these normalization constants exactly the way I've done it, okay, is often very painful. Okay? Often, what you do is the following. Okay? Often what you actually do is the following. See, suppose I wanted some evolution from x initial to x final. Suppose I wanted this evolution from x initial to x final. What you can do is to look at the sum over all paths as the classical path plus fluctuations and integrate over the fluctuations. Okay? And no approximation. Okay. Now, the big difference is that between since the classical path already has the right boundary conditions, the fluctuations are a problem with boundary conditions 0 and 0 at the initial and final times. Okay. Now, let's suppose we were working on, let's say, the harmonic oscillator. So what would we be doing? We would be looking at paths. We would be doing some path integral over fluctuations. Okay. We would be doing a path integral over fluctuations. Starting out at time 0, ending up at time t, with the boundary condition that x is 0 at time 0 and 0 at time t. Okay? Now, there is a convenient basis for such functions. The basis is sine functions with the right periodicity. Okay? And what you can show is that this measure that I do, just by formal Jacobian terminology, okay, is the same thing as the following. Suppose I take x of t and write it as sum over an times the sine n times y. Then this measure dx1 times dxn minus 1, okay, is the same thing as the measure dan product over. No, without. Okay, and now because I've ignored the normalization, now it's no longer true. Okay, now it's no longer true that the path integral that I started with is exactly what I wanted to compute. It's true after normalization. Okay, so if I define the path integral in this manner, okay, then I will need to add a counter terminus. Okay, and this is often the operational definition of the path integral, just because that object is a bit tricky to get to work with. Okay, so I'm sorry, what I said was wrong initially. This is the correct version of it. This is the problem I had in mind. Okay.
So the counter term is always like very big.
In this case, it's basically a vacuum energy counter. It's a trivial counter. In quantum field theory, when we understand these things, everything will be less trivial. We'll come to that. It won't come just from these trivial things about changing a path integral into a. It'll come from more interesting things. We'll come. Okay. Thank you. Any other questions or comments? Okay, great. We've been able to take this evolution operator and represent it as the path integral. And the path integral took this nice familiar form. There's the sum over all paths, weighted by e to the power times exponential of the action. All of you know this, of course. This was a review. Okay. Any questions about this before we'll immediately start applying these ideas now to quantum field theory. But any questions? Okay. So let's start. Now, everything.
Sorry. Is what you calling path ordering what we normally call time ordering, or is something slightly different?
Path ordering is same. Yes. The path is just an evolution in time.
Okay.
You can consider other evolutions. Right. But it's the path order exponential.
Yeah.
So, whatever notation you use, what you mean is product of infinitesimal evolutions. As long as we agree on that. Okay. Excellent. So, let's keep going. Now, everything I said here would work for two particles. Everything I said here would work for any particles moving in any number of dimensions. Okay, I just worked one particle for notational simplicity. Nothing dependent on it. Okay? So any action of this form with arbitrary numbers, okay, any action of the general form. Suppose you start with the classical action of the general form. Aij xi dot xj dot, okay, plus v of xi dt. Okay, everything we said would go through basically without modification. Okay, I wouldn't need more notation in the complete set of states with labels for each of the frameworks. Okay. Now, in quantum field theory, we often end up studying such actions. So let's start with the simplest action one that you're familiar with, one that you studied in your earlier courses. Suppose we started with an action which was the following. It's the action for a scalar. Okay. So, let's set conventions. Let's choose in this course to work with the mostly positive convention for the action. So eta is -1, 1, 1. Okay? And there are advantages to either convention, but we try our best, to the extent that we can get conventions right, we'll try our best to stick to this convention. Okay? So now, what is the kinetic term for the scalar field? Well, because the time part is, so I'll write down the basic treatment. It's d mu phi, d mu phi. Right. This is the correct kinetic term. Because if you work it out in terms of phi dot, this will have a positive phi dot square. That's the rule for action. Actions are going to give rise to unitary quantities. Always come with positive kinetic. Like x dot squared. Okay? Moreover, now the position square. So this is equal to phi dot squared by 2 minus del I phi squared by 2. So both things are satisfying. First, that the kinetic term is positive. Second, that the term that is purely potential is negative over positive definite quantity. Okay? So the thing that we identify as v of x is del I phi squared by 2, which is positive. Okay? And let's say that we include here, to start with, some minus v of phi. Okay. The minus v of phi will, most importantly, will be phi to the 4. But at the formal level that we're going to work, it won't matter. Okay? Now, this is a beautiful Lorentz invariant action. Okay? But just for intermediate steps, I'm going to do something that no physicist, no theoretical physicist likes to do. This is more the symmetry of the problem by working with a particular slicing of time. Okay? So I choose some particular choice of time, whatever that is, and I slice up my path integral according to that slice of time. That slicing of time. With that choice of time, the action is what we have written. It's plus phi of x dot squared by 2 minus del I phi of x squared by 2 minus v of phi. And this is d dx. We're working in some d-dimensional space-time. Okay. Now, this looks a little confusing because we've got a continuous number of degrees of freedom. But, in order to make sense of this theory, we can imagine regulating it by a sort of lattice type regularity. Okay? So imagine that x is not continuous but discrete. We'll eventually take the spacing to 0. That's basically what we mean by this theory. Okay? Then, what we've got, imagine also for a moment that we put the whole theory on a spatial terms. Okay? Then, this action here is exactly this one. With the xi's, the role of the xi's being played by phi of the various discretized spatial points. Is this clear? Since our derivation of the path integral went through for any action whatsoever of this form, I put it on a torus just so that there are a finite number of degrees of freedom. Okay? We'll eventually take the torus to be as large as you want. Okay? Since it's true for any action of this form, it's true also for this action. So without further ado, we conclude that the evolution operator for quantum field theory, just like in quantum mechanics, okay, is given by e to the power I times minus d mu phi d mu phi by 2 minus d mu phi. Now let's be a bit careful. D phi of x. Okay? This is Lorentz, this x position and time. Okay? So, what do we mean? You see, what do we mean by this? What do we mean by all these quantities? This quantity is pretty clear. It's the action. What we mean by this quantity here is a path integral over phi at various time positions and at every space position. You see, because space now plays the role of the label. So you have to do the path integral over each of the label variables. So each spatial point. And then space, the time is discretized according to the velocity of the path integral. Okay? So the way that we make sense of this, imagine that you've got a grid in space-time. Okay? The spatial positions of this grid are this I index. The time positions are what we did before. Okay? We had to take a product of integrals over each time, but for every variable. So that means a product of integrations over every point on this grid in space-time. Okay? So that's what we denote formally by this path integral circle. It's the integral over all functions of space and time. And notice something quite beautiful has happened. Two beautiful things have happened. Even though we started, we took this nice, beautiful classical Lorentz invariant theory, and in order to try to set up some evolution operator, in order to set up some evolution operator, we broke the Lorentz invariance of the problem by choosing a time slicing. The final answer we gained to the Lorentz invariance. You see, the measure involves product over all fields and all points of space as well as time. Basically, not distinguishing between space and time. Okay? And the action was the action on which, unlike the Hamiltonian, for instance, is manifestly Lorentz independent. Stuff. Okay. Now, what do I mean by this evolution operator? What do I mean by this evolution operator? The evolution operator is, is precisely as it was in quantum mechanics. If we want to know what is the amplitude, okay, so as we've discussed, in quantum field theory as in quantum mechanics, we've got a Hilbert space. I should have said this more clearly, let me say it more clearly. In quantum mechanics, the problem we discussed, we had a simple Hilbert space. The Hilbert space of square integral functions of x. Okay? If we generalize this quantum mechanics to this problem, we have where I is equal to. We also have a nice Hilbert space. The Hilbert space of square integral functions of the m variables, x sub I, x1, x2, up to xn. Okay? Now, once again in quantum field theory, at least with this discretized, once we've discretized, we've got a Hilbert space. The Hilbert space is the we will see different ways of looking at it. Since you've done a lot of Fourier analysis in your quantum field theory one, you already know many different ways of looking at it. But one conceptual way of looking at it is just square integrable functions of phi at each point in space. Square integrable functionals of phi. What's a functional? A functional is an object that takes a function and outputs it. Okay? So for every value of this function, you have some number. For instance, an integral is a function. You've given a function, you associate a number with it, like the integral. Okay? So square integral, so Schrodinger wave functions of quantum field theory are functionals of phi of spatial x that have some square integrable properties. Okay? This is the Hilbert space of the theory, just starting from the original canonical definition and canonical framework after you discretize it. Okay? And now, just like you had position eigenstates x, which have the property that the operator x acting on x is number x acting on x, you have position eigenstate states phi of x, which have the property that the operator phi of x acting on this is equal to phi of x. Notice that the Hilbert spaces at distinct points in position are distinct Hilbert spaces, and that the operators phi of x at different positions on a given time slice all commute with each other because they are operators that act on different Hilbert spaces. Okay? So it is possible to simultaneously diagonalize these operators because they don't commute, meaning simultaneously meaning at all points in x. And so there is one basis state such that phi of x at any x on that phi of x is a particular function of x. Is this clear, or was my notation too confusing? If this is, I'm sorry, I said this in a very confusing way, I know. If it was unclear to anyone, please.
So do you also need to put in the constraint the phi of that phi of x needs to be square integral?
Yes, you would need to do that. So this for a wave, this wave functional is a wave functional on the Hilbert space is that of square integrable wave functionals. Okay, and we will do this automatically in the way we actually use this by going through the basis. Yes. Any other questions? Is what I'm saying clear? Do you understand what I mean by this state in quantum field theory?
Requiring that the wave function is square integrable, does it some sort of restriction on the kind of field configurations it can have?
Yeah, right. It's very much like in quantum mechanics. Basically, you will not. You see, what does it mean, roughly speaking, in quantum mechanics? What does it mean that the wave function is square integral? More or less, it means that it dies out at infinity. Okay, that's the same kind of thing that's going to happen. That the functional has no support when phi is taken to be to infinity at any x. Roughly speaking. Yes. You have to do this more carefully. There's major issues and you kill yourself with the problem. But roughly, this is what it means. And then it doesn't blow up if the field goes to infinity anyway. This dies off every infinite time. Roughly, that's what we do. Okay. Now, of course, you know, if there's I sometimes given courses to in places where mathematicians also attend. And then we get into real trouble through all of this. Because you say that the Hilbert space is square integrable, then you use these x's, which, as you know, in quantum mechanics are not square integrable. Because you square a delta function, you integrate to get infinity. Okay, so let's put all that aside. Okay. You know what I mean? Like, you know, most of these things cancel out. Places where they don't cancel out, usually it's the physics that helps you understand why it doesn't cancel out.
Sorry, but at each point you said there is a Hilbert space, or what?
Yes, at each point there's a Hilbert space.
So how do I find out the dimension of that Hilbert space? Or, how do I find out different states of that Hilbert space at each point?
At each point, the Hilbert space is simply obtained by the harmonic oscillator. You see, at each point we've got a Hilbert space, which is square integrable functions of phi of that value x.
Exactly like a 4 vector, right? 4 vector.
No. You see, when we talk about Hilbert spaces, we always slice it.
Oh, yeah. So these are type of.
You see, Hilbert space. Think about quantum mechanics. A Hilbert space is not defined in time. It's defined once and for all. That's the same thing's going to happen. So we take time slice. So at each point, it's spaces. Okay. I only need to give time slice. Such is not unhappy with something. Go on.
So if I want to find out, I have to quantize, or I have to put I mean, in terms of, you said that the harmonic oscillator, I'll be able to find out. Is that just?
No, go on. Sorry.
So how do I find out the number of states?
The number of states is infinite.
Yeah, number of states is infinity, and I mean, how do I say precisely what are my states?
What are your states?
Yeah.
See, suppose we take this thing and on a lap, we take space and break it up into lengths. Let's say space is one dimension, so I can draw on the board. Okay? So there's x1, x2, up to xn. Let's say we're on torus, so xn is infinite. Okay? So, what is our Hilbert space? Our Hilbert space are just square integrable wave functions of phi of x1, phi of x2 to phi of xn. Okay? Now, what's the Hilbert space? Now, if you want to specify, one way of specifying a state, okay, one way of specifying a state is just to specify a waveform like that. Some function of phi of x1, phi of x2, phi of x. Now, suppose we're doing free field. I want to know what is the specification of the vacuum. In fact, it is a function of this form that you can easily write down. Okay? But of course, this is not a convenient basis for specifying the vacuum or any reasonable state. Because while the Hilbert spaces are distinct, the Hamiltonian is not a product of Hamiltonian. It's not a sum of Hamiltonians in different Hilbert spaces. Right? Because we've got this del I phi, del I phi. This thing is phi of x n minus phi of x n minus 1 by 2 the whole thing squared. So while the Hilbert spaces are completely distinct, dynamics doesn't factor into dynamics in the Hilbert spaces. Okay? So this way of thinking is not usually the most, at least in weak coupling, it's not usually the most convenient way of representing states in the Hilbert space. It's more convenient to go into a basis that diagonalizes the Hamiltonian, which, as you know, is the Fourier property to do. But just about the issue of Hilbert spaces, maybe I haven't understood your question.
No, so the final statement, at each point I have a Hilbert space
Yes.
with the same dimension.
Same dimension.
And I can find out the.
Because the dimension is infinite.
Yeah. But I can find out them by the procedure you just said. I just have to find out the harmonic oscillators.
I mean, I wouldn't use harmonic oscillator, but yeah, square integrable wave function.
Square integrable.
Good. Any other questions? Okay, so why did I start saying this? I started saying this because I wanted to tell you what is this object. Okay, so I was a little cavalier in the boundary condition. So let me. So this object, let's say I integrate from time t1 to time t2. Okay. Now, in order to make this well defined, I need boundary conditions on this integral. Just like in quantum mechanics, in order to make the positive type well defined, I needed boundary conditions at initial and final times. Okay? I need to say what x was at initial and final time. Because this action, once you discretize it, is not well defined unless you know what's happening at the boundaries. Okay? So this object is only well defined if I specify that at t1, I know what the function is. Some phi of x. And at t2, I know what this is. Some phi 2 of x. Is this clear? Then, this object now is a clear number. And the interpretation of that is phi 2 of x e to the power minus iht. Phi 1 of x. Well, these states we defined 2 minutes ago. The eigenstates of the object.
Do the boundary conditions break the Lorentz?
Yes, the boundary conditions break the Lorentz invariance because we're asking a question that breaks the Lorentz invariance. We're asking a question: what is the amplitude for a state defined on this slice to evolve to another state defined on the other slice? Since that question breaks Lorentz invariance, the boundary conditions have to. Okay, but the basic object of which we're computing, the fact that there is a basic Lorentz invariant object appearing, as you will soon see, will give us a lot of, will be very nice. Will easily enable us to derive many Lorentz invariant identities. It's conservation concept, as you see. Okay.
So,
Yes.
So we are defining, as you said, the Hilbert space on a slice.
Yes.
But that will be sufficient only when we have an evolution equation of the functional, like a Schrodinger equation, means the first order in time derivative.
Right.
So what guarantees that to be a case?
Well, we're doing quantum mechanics. Quantum mechanics always has Schrodinger. You see, all that quantum field theory is souped up quantum mechanics. You take everything, discretize. And then you've got quantum mechanics of a large number of degrees of freedom. And quantum mechanics is governed by the Schrodinger equation. I bar del psi by del t is equal to h psi. Okay? The differences arise in what Hilbert space you're working in. What h is. Okay? And here we're working in a pretty complicated Hilbert space. The Hilbert space of square integrable wave functionals. And h acting on this Hilbert space will be a little complicated. But we're always doing, your quantum field theory is not an extension of classical quantum mechanics. It's a specialization of quantum mechanics. Okay? And so, we have the Schrodinger equation. This is here? Go.
As you pointed out, whatever states we interested in, like the vacuum, will be some very complicated superposition of these 5 states.
Yeah, we'll write this down at some point.
Yeah. The point is, what if you wanted to write the amplitude for going from a vacuum state to a one particle state? This would be really bad.
Well,
because you have to, your basic objects are these matrix elements.
are these matrix elements? But you see, now suppose, let's ask this question in quantum mechanics first. Okay? Even in quantum mechanics, let's say for the harmonic oscillator, the eigenstates of the harmonic oscillator, or any state you might really want to consider, is pretty far from position.
Yeah.
For the path 10. So how do you, suppose you can ask, suppose I was actually interested in psi 2 e to the power minus iht of psi 2. Not in x1 extent. Then what should I do? Well, you just use the same thing that we always do. That is, put an xf, use completes.
Yeah.
Okay? And e to the power minus iht, xi. Okay? This is the 5 minutes to calculate. What you have to do is convolute it against the initial wave and the final wave.
Those will be extremely hard. Yeah, what I'm thinking was those will be extremely complicated to write down and
well, those would be extremely complicated to write down. Okay, in the harmonic oscillator, these will be Hermite quantities.
yeah.
Okay? In quantum field theory, if you were really interested in computing some finite time evolution, it's true it would be a bit harder. It's not that hard to read coupling. It's not like you ever want to do this. You rarely do it. Okay? But it's not that hard. You see, we'll write this down at some point. We'll write down the vacuum wave function of scalar fields in this language at some point. And you'll see, it's some exponential of integral stuff. It's not too dead. But let me emphasize one more thing. Path integrals in quantum field theory, and often in physics, have used not so much because the integral is easy to compute. Okay? In fact, you almost never almost never exactly compute a path integral, except when it's constant. Okay? The one exception actually is for supersymmetric field theories, where you can use the tricks of supersymmetric to exactly compute path integrals by clever ways. One exception. But you almost never use the path integral, to actually evaluate the integral. Okay? However, the representation of various quantities as a path integral is a device that allows you to transparently see formal connections between various things. That is the main use of the path integral. Okay? So it's a very useful object to have in your head so that you can understand the properties of various things. Okay? Actual computations, of course, you'll see. Yeah, you'll see the actual path integrals you ever actually compute are basically Gaussian. And then you compound them with perturbation theory or you do other things. Okay? So, right.
Sir,
Please.
when we are slicing up time, we are assuming that at every point there exists a Hilbert space.
Yes.
So what guarantees are that there exists?
So wait. At every time there exists a Hilbert space.
At every point of space.
There exists a Hilbert space which lives for all time.
Okay. So, and we are assuming that there exists a state basis out where phi x is diagonal. Are we assuming that?
No, we're not assuming that. You see, what we're doing is just canonical quantization of this Lagrange. Suppose I gave you this Lagrange, and I asked you what is the quantum mechanics according to the usual procedure that the classical Lagrangian gives you. What you would tell me is, well, what I have to do, I've got m different variables. The variables are xi's. Then I set up the classical mechanics in canonical formulation. Okay, and I do the usual correspondence. That will give me a Hilbert space, which is square integrable functions of x1, x2, x3, x4. Okay. Now, this field theory Lagrangian, once we have discretized, is exactly of this form, where the role of xi's is played by phi's at different positions in x. And therefore, the usual procedure of Dirac correspondence, going from a classical theory to one, okay, tells us what the Hilbert space is. The Hilbert space is the Hilbert space of square integrable functions of x of the various points of space. In the example we set up for one-dimensional lattice, x0, x1, up to x0. I say this is it. Phi of this, phi of this, phi of this. Just the standard rules lead us to this conclusion. Correct. Now, what is the operator phi? The operator phi acts purely in this Hilbert space. Phi of x0 acts purely in this Hilbert space. Phi of x1 acts purely in this Hilbert space. Okay. So that these operators commute with each other is automatic from the usual rules. If by assuming you mean, are we assuming that the usual rules apply? We're assuming that. But we're assuming nothing. Okay? What we're doing is using the usual rules to set up a quantum mechanics, a quantum system. Okay? Now, how could that go wrong? It could go wrong in one of two ways. A, it somehow is not internally well defined. B, there's some ambiguity. Okay? The second thing actually often does happen. it's something that one should keep in mind that quantum mechanics is a bigger theory than classical mechanics. Okay? So it's usually, it's often not the case that you can uniquely answer the question, what quantum system has this classical system as the classical limit? There may be many answers to the question, often are. Okay? So if you're worrying about the ambiguity, that's a fact of life. What we're doing here is producing one sensible quantum definition that will have the right classical limit. We address many of this question of the ambiguity further. Then there is also the question that you're asking, that you could implicitly be asking, is this theory well defined? Now, once we've discretized, what we've done is clearly the issue is taken away with discretization. Take the continuum limit. This may or may not be well defined, and in fact is a very tricky thing to get straight. That's the program of renormalization. Okay? But permit me for the moment to discretize that everything we've done is kosher. The question of taking the continuum limit is an excellent question which we'll come to soon. Soon, of course. Okay? But not today. Okay? But so if your question was about those subtleties, they're deep subtleties. We'll deal with. But if the question was about a more elementary thing, well, not making any other. It's just following the usual rules. Okay? Other questions, comments? Yes?
So, you said that Hilbert space for single time, like Hilbert space at x0 commutes with the Hilbert space at x1.
Yes, these are spatial positions.
Same thing happens for two different
It's not, actually, even the word commutes is wrong. It's just the full Hilbert space is the product of Hilbert spaces, one at each location. Operators commute. Hilbert spaces are obviously, if you've got a product of Hilbert spaces, you've got one operator that acts only in one of these Hilbert spaces, an identity in the others. They obviously commute with each other. This is not, something that's hard to see. It's obvious. Okay? Those of you who've been interested in entanglement entropy, this is the basis for that whole idea. That it's obvious in quantum field theory that the Hilbert space, these are regarding subtleties about gauge theories. Okay, that the Hilbert space is a product of Hilbert spaces, one at each point in space. So you can define an entanglement entropy associated with the region in space, because that region in space is associated with the sub-Hilbert space, namely the Hilbert space of all degrees of freedom in that region. Okay, any other questions about it? No, we're just looking at a transition amplitude within one equal. Okay? These two x's? Yes. No. You see, what we're asking for is a matrix element. So let's forget these two. Your question can be addressed just about this one, right? Okay. So what we're asking for is a matrix element. You see, we've got a basis of states in the Hilbert space labeled by this number x. For any operator A, we can ask this matrix element where x and y are not equal. That's all we're doing. We're looking at the matrix element with x label on one side, y label. Is this clear? Okay? This matrix element enables us to compute the more general matrix element. So any operator, we don't need to work on a basis, we can compute psi 1 on one side and psi 2 on the other side. Right? So that general basis matrix element is related to the special one that's easy to compute. It goes by convolution with wave functions. Is this clear? Okay, excellent. Okay. Now,
sorry,
yes.
So that particular object which is the amplitude is actually a transition from phi 1 defining that all x's and t1 up to phi 2 defining that all x's and t2.
Exactly. Yeah. It's this phi 1 tells you that operator phi acting on that state is phi 1 of x at each x. Okay? Now, of course, in general, you would want the analog of the psi 2 times u, Salesian operator times that. this, you can go to this by convolution. Psi 2 times phi 2 of x, phi 2 of x, u phi 1 of x, phi 1 of x, psi 1. This is some wave functional. This is your Schrodinger wave functional for the final state. This is your Schrodinger wave functional for the initial state. Just go take that Schrodinger wave function and do the integral for d phi 1 of x space, d phi 2 of x space. That gives you the transition amplitude between any two states. Is this clear? But other questions, comments? Okay, excellent. Now let's move on to something a little less straightforward. So we want, okay, as we will see, maybe in the next lecture, or maybe depending on when they come in, as we will see, this path integral representation is very useful to derive many formal properties. Okay. I mean, it's a very useful thing to have. So, when we started, we worked out this path integral representation with a scalar field. We find it very useful. So, we're sort of determined to write down some path integral representation for every field theory we study in physics. Or we try. Okay. Now, so if you try to think about the theories that are qualitatively, if you to do a field with 2 scalar fields and 10 scalar fields, that's the same thing. Okay. Where do you have qualitative differences? Well, you could have qualitative differences if there's something funny in the kinetic term. Or you can have qualitative differences if you're dealing with firmness. So these are the 2 problems we're going to address one at a time. Okay. So now, of course, we don't want to spend a lot of time dealing with some artificial theory. So you can ask, is there some theory with bosonic fields that, for some natural reason, has different structure of kinetic terms than we have for, let's say, 5 scalar fields or 4 scalar fields? And if you think about it, you know one theory very well that does. This is the theory of electromagnetism. Okay, gauge theories. Okay? So, since you've not, much of what I say just goes through directly about the non-abelian theory. But since you've not discussed the non-abelian theory, we'll be doing that in detail. Let's stick to the abelian theory for 5 minutes. Okay? So, the theory we're going to address is the theory based on the action S is equal to let's start with pure electromagnetism. So, and now I've got the sign for it. And the answer is no, I have. Let's check. We'll check whether it was sign. Okay. Let's define F mu nu firstly. F mu nu is equal to del mu a mu minus del mu a mu. Mu and nu indices run over all space and time directions. And we're in arbitrary dimension. Arbitrary space time dimension. Okay. Now, this action has a funny kinetic term. Okay? In order to see, for the purpose of quantization, in order to see what I mean by this, let's do this time slicing. We'll single out 0 as special. Okay? If we single out 0 as special, we can rewrite this action as F0i, F0i. That's half minus this. Okay? Plus 1 by 4 Fij. just allowing this mu index to include time. I mean, taking out the time, the terms in which time appears especially. Okay, dx. Now, something that you see here immediately is the following. Firstly, Fij is del Iaj minus del Ji. It involves spatial derivatives of AI. So this is potential. It's the analog of the V of phi. That we know. Okay? This roughly is the analog of the kinetic. Okay? But let's write it. This is del 0 AI minus del I A0 with a plus because I'll write everything lower. Del 0 AI minus del I. It's all this thing squared. Why is it kinetic? Does it do stand? Why didn't we have a half, you're asking? It's because in this contraction between mu and nu, either mu could be 0 or nu could be 0. That is an additional factor. Okay. It's in order to get standard half for kinetic term that we put the 1/4 conventionally. Okay. Now, notice here that this has a del 0 AI and the whole thing squared plus half. So the AIs have a standard kinetic. But A0 has no kinetic. There's no term that involves time derivatives of A0. Okay, this is obvious if you think about what F is. Right? F is completely antisymmetric of derivative of the A. And del 0 A0 is not antisymmetric. Okay. So now we've got something interesting. Okay? So the question we're going to ask is the following. Suppose we write down the path in F, but this is such a beautiful action. Such a beautiful action. And we've just learned that one way of defining quantum mechanics is in terms of path integrals. Okay. So what we're going to ask is the following. Suppose you might have been tempted originally. You might have been tempted originally to say, well, if you didn't know about this first class constraints and blah blah blah, you might have been tempted to say that the canonical procedure suggests that this is a very strange action for quantum mechanics. It's not, and you can deal with it, of course. But that might have been your first reaction. However, from the point of view of classical action, it's beautiful. And therefore leads to a beautiful path integral. So what we can try to do is the following. What we can try to do is to say, let us take this beautiful path integral as the definition of our theory and reverse our logic. Let's try to understand what Hilbert space interpretation this path integral has. Does it have the Hilbert space interpretation? And if so, what is it? Okay, so that's a question we're going to address now. So we have e to the power I times minus f mu f mu by 4. This is the path integral we wish to consider. And the question we are going to try to address is what Hilbert space does this? Is this a path integral that defines the quantum mechanics? If so, and what Hilbert space? Okay? Not completely straightforward because A0 does not have the standard kinetic terms. Okay? So let's proceed. So this path integral here is dAI dA0. And because we're interested in Hilbert spaces, we're interested in some slicing, so we're slicing in time. So time and A0 are coordinated. It's the same 0 inputs. Now, suppose I looked at this path integral in this way. Because I don't know what to do with A0, I will do the path integral over A0 last. Okay. So I think of it as integral over A0 times integral dAI. Okay? Exponential of Del integral I. Oh, I've already said drop. I'm not going to drop h bars. Okay, we restore them dimensionally. This is the traditional thing to do in quantum field theory. Just because it's traditional, it's hard. No, it's hard not to follow tradition. Okay. If it wasn't being recorded, I would. I would make some comments about textbooks in Gujarat. Okay. But okay. So, I times exponential of what is it? First it becomes kinetic term, so integral as an I d0 ai minus I 0 over squared 2 plus minus del I aj minus del j I. And you understand that this is summed over I and this is summed over ij. This is our action. Now, while the full path integral is confusing from the point of view of a Hilbert space, if we look at this part, if we look at this part of it, that part looks totally standard. Because each AI has a standard kinetic term. Okay? So if we just wanted to give a Hilbert space interpretation, this part of the path integral. Okay? We would follow the usual procedure. What would the Hilbert space be? The Hilbert space would be wave functionals, square integral to wave functions, over AIs at each point in space. Each of the d-1 AIs, or 3 AIs if we were dealing with, we were living in 4-dimensional quantum physics. 4-dimensional next.
Sorry, but by standard what you mean here also I will have a linear term in del 0 ai, right?
You will also have a linear term in del 0 ai, but that is not a problem. As long as the action was quadratic in time derivatives, that whole derivation went through. For instance, in quantum mechanics, in the presence of background electromagnetic field, AI, you have a linear term in this kinetic in x dot. Okay? I did deal with it, but it's totally trivial too. What was important was that it was quadratic. Yeah. Okay? Now, A0 here is an arbitrary function of space and time. Because we're going to do a path integral over all these zeros. Okay? But this goes back to your question. Tell me your view. Ritam. This goes back to Ritam's question about the harmonic oscillator. He asked if V of x was a function of time, could we do the same thing? Of course we could. So this object here is going to give us a standard path integral. It's going to give us a standard Hilbert space for a system that breaks space-time symmetry because of some background field. Who cares? Okay. So what is this quantity computing? This quantity, of course, is computing the evolution operator. Okay? And let's go. So evolution operator, as always, is e to the power minus I h times t. Let's compute what the Hamiltonian for this object is. The Hamiltonian of this space of square integrable functions of AI at each point in space. So what is the Hamiltonian for this object? Well, we just do standard stuff. What's the Hamiltonian? The Hamiltonian is pi. So what's the momentum conjugate to AI? It's clear, right? The momentum conjugate to AI, del 0 AI minus del I A 0. More precisely, the momentum conjugate to AI at x is this object at x. Okay? And And I'm going to deal with so let's suppose I define this. This is phi I of x, will be this. And we will have the commutation relations ai of y space times phi j of x is equal to delta ij times e minus 1 x minus 1. Okay. The normalization of this commutation relation is because the action has little delta x's, which we don't take into account. Is this okay with everyone?
There is I.
Is this okay with everyone? Okay, great. So we've got I. Yeah. Now let's obtain what the Hamiltonian is. The Hamiltonian, what is it? It's integral ai dot phi I minus the Lagrangian. Hamiltonians are supposed to be written in terms of coordinates and momentum. Ai dot is not in terms of momentum, and that's easily fixed. So h is equal to this. H is equal to, let's write ai dot. Oops, what did I do? Let's write ai dot as pi I minus pi I plus del I of t. Just from this relation. Okay. So h is equal to integral. Now pi I squared. Now when you work out this pi I squared, and then the Lagrangian has a plus pi I squared by 2. So this is now the first term of the standard. You get pi I squared by 2 plus fij. This is the Hamiltonian coming to the first term. But in addition, there's a second term. And the second term is plus del I 0 times pi. Okay? So what does the path integral evaluate for us? The path integral evaluates for us e to the power I h, e to the power I times this object. Times d times plus del I is 0 pi. You know this. Okay, this integrated over space time gives you the times t. Okay, so you see the only place where A0 enters the physics of this auxiliary, the quantum system we get from this auxiliary path integral, is in this term. This by itself is a totally standard kind of system, right? It's a path integral for 3 scalar fields, A1, A2, A3, with a particular potential, namely Fij. Totally standard. But the system depends on this one additional A0 field, which in our auxiliary problem was background. Okay? And that affects the Hamiltonian.
If I treat A0 as some arbitrary field, as far as I'm concerned with AI path integral,
Yes.
This might make the Hamiltonian non-positive.
This might make the Hamiltonian non-positive definite. No, I don't think so, because you see, okay, might be non-positive definite, but it won't make it really now. Because this term is quadratic. So, I mean, it will be completely, bounded well defined. Right. Okay.
Sorry, but pi i's though they are conjugate to AI, but pi I contain AG, right? So how do I think about?
What? No, but you see, that's not how we should think. That's not how we deal with conjugates. Pi I is an independent operator. Pi I is the operator that obeys this computation. Okay.
But while writing path integral, these are just numbers, right? I mean, I don't.
Yeah. No, so we have a path integral which was this.
Yeah.
Now what I'm trying to do is to understand what that path integral is computing.
Okay.
So the claim is that this part of the path integral is computing the evolution operator generated by this Hamilton in the Hilbert space built out of 3 fields. Square integral functions of 3 fields. Okay? Straightforward. No confusion here. But now what are we supposed to do? Now what we're supposed to do is the following. Now what we're supposed to do is to implement the path integral over AZ. Okay? Now what does the path integral over A0 do? Provided I'm allowed to integrate by parts. And, well, up to boundary that Sachin will tell you a lot about. Okay, which we ignore. Provided I'm allowed to integrate by parts. Okay. Maybe. No, actually, I don't even want it. Sorry. So just let me leave it. Okay. What is this objective? Okay. You see, now if I integrate over all A0, something quite interesting is happening. Okay. Let me explain the interesting thing with an analogy first. Suppose I had e to the power I times PA, where A is a number, in ordinary quantum mechanics. And I have to put this on psi of x. On some wave function psi. Suppose my wave function psi had a Schrodinger representation psi of x. Then, as all of you know, this object is the translation operator. Okay? This object is a translation operator. The reason it's the translation operator is that this object is conjugate to position. It generates translation. Exactly. Yeah. So this object here is psi of x plus a. Now, if I took this object and integrated over all a, what would I get? What I would get is psi of x plus a integrated over all a. If I wrote out the most general wave function in Fourier space, let's say we were on a torus symmetric discrete. If I wrote out the most general integral in Fourier space, then this is the projector onto a particular state, namely the state that is translation invariant, the state that has zero Fourier motion. Okay? So this starting at x1 and ending at x2. Okay. Now, the basic idea, the key idea, well, the key point was this. So this is the operation that we will sometimes, in words say is the amplitude for propagation of the particle from x1 at time, let's say 0, to x2 at time t. Of course, I could have equally said x1 at time t1 and x2 at time t1 plus t. So this translation is invariant. Time translation is invariant. Now the key observation here is that this operator can be built out of breaking it up into operators for evolution over smaller times. And the identity is the completeness of states of quantum mechanics. This is true always. This is just a true statement of decomposition of the identity at a basis. Okay? So, at any point of time, we could rewrite this operator as e to the power minus IH, let's say, T1, T minus T1, as e to the power minus IH, T1, times X1, is trivial. I've used the fact that these two operators commute because H is the same H. Okay. And then I can insert this identity into here. Okay. Now, once I insert that identity into here, so let's call this object G of x1 to x2 in time t. Clearly, what we get is the identity that G of x1 to x2 in times t by inserting this our identity is equal to the integral of G of x1 to x in time t1 times G of x to x2 in time t minus. Is this clear to everyone? Okay. So the lecture today is going to be about path integrals and their use in quantum field theory. So I'm going to start by reminding you how path integrals work in quantum mechanics. Okay. So suppose we have this is elementary stuff, most of you know it. We're just going to print this. That's just notation. Okay, so suppose we had a quantum system with an Hamiltonian which was E squared by 2m, and that's V of x. The canonical first quantum mechanical system anyone studies. Okay, it's the quantum mechanics of a particle moving in one dimension with canonical kinetic term and some potential. Okay, now as all of you know, the evolution operator in quantum mechanics is e to the power minus IH for h times t. Okay, this is something called U of t. And it's the operator that takes a state at time t1 to a state at time t1 plus t. Okay? So suppose you know your state, your state is psi at t1, and you want to know what is the state psi, what is psi at t2? The answer to that question, as all of you know, is e to the power minus I. Solve the Schrodinger equation h of t2 minus t1. This evolution operator is clearly a useful thing in quantum mechanics. It's the operator that allows you to translate things in time. It's the operator that allows you to ask the basic question of all physics, that is given a state at any time.
Without the t, right?
Thank you. Given a state at any time, what is the state at a future? Okay. Now, as all of you know, over what is it, 70 years ago now, Feynman came up with a very nice path integral representation of this evolution operator, which we will now discuss. Okay, so this is an operator. The operator has two indices. We're going to try to represent it by a number. The only way we can do that is look at matrix elements. So let's suppose we are interested in the matrix elements of the operator, e to the power minus IHT, break it up into those products of those various evolution operators, and between each of them insert the complete set of states that we discussed. Okay?
Don't get integral imply integral also over t, because you are like breaking the integral into.
We're breaking the integral, but it's going to be a product. So let's write.
One term will cancel the other. That's entirely different.
No, let's write the formula. So the formula is that G of x initial to x final in times t. So what is it? So now we will have a product over all intermediate times. So m is equal to 1 to n minus 1. Okay. G of now x n minus 1 to x n in time t n minus what we call delta. Okay, and then g of x xf, xi, xf, computer integral with the dx n. Okay, so I've got n minus 1 guys. And what have I missed here? I've taken this from 0 to 1, and then if this is only up to n minus 1, sorry, this is m. Let me write this list fancily. dx1, dx2 up to dx n minus 1, and then these g's, there is a product that is equal. Okay. So what we have is a product of n factors of evolution, because we've broken up the time interval into n little subintervals. But because we've broken this evolution operator obeys this property that if you know it for smaller times, you can build it up for bigger times by compounding and integrating. Okay? So then finally observe that since this was the case, we could try to repeat this procedure many times and build it up out of compounding infinitesimal time evolutions. Okay? So what's the idea? Let's suppose we call this okay. So suppose we define various time steps. So let's say that for simplicity this is at time 0, notation. So we have x1 at time 0. Now we break this up into many small time steps. Let's call the first time step. Okay, I should have called this T1 because in conflict with my notation. Let me call it U. This is U. Okay, let's call the first time step T1. That T1, let's say that this, and let me also put this X, initial and X line. Sorry. So suppose it's an x0 at time t0, which is 0, and we'll call this x1 at time t1, x2 at time t2, up to xf, xn at time tn, x1, xf at time tn, which is equal to. Okay, so what we're going to do is break up this evolution operator into, and we're going to use the notation that delta t1 and delta tn m is equal to tm minus 1. What we're doing is breaking up this entire interval from 0 to t into n different subparts. Okay, so the first subpart is at t1, the second subpart is at t2. It's between 0 and t1. The second one is t1 to t2 up to t n minus 1 to t. Okay, so then we take this evolution operator on n level subintervals. There are n minus 1 intermediate positions, and we have to integrate over those intermediate positions. Okay, this is an obvious idea. And Feynman's main insight, following up by an observation by Dirac, was that when this thing is infinitesimal, I mean each of these infinitesimal guys are rather easy to compute. So let's go ahead and compute. Okay. So, what we want to do is to compute this evolution operator. We want to compute, let's say, b e to the power minus I h delta t. And then, when delta t is now some infinitesimal object, we want to work to first order infinity. Okay? And the other way to do this computation goes as follows. The first thing to do, I rubbed out this h, but you remember, it's p squared by 2m plus b of x. And the first thing to do is to remember that in general, you cannot, it's not true that e to the power p squared by 2m plus b of x, in general, times on t, is not equal to e to the power minus I times p squared by 2m t times e to the power minus I times b of x. See, this is not true. The reason is that p squared and b of x is commute. Okay? However, and this is what makes the finite evolution difficult to evaluate a function in the non-commuting nature of various operators. Okay, however, if this t was an infinitesimal, the lack of commutation is expressed by the Campbell-Baker-House law of identity and involves the commutator of this operator, p squared by 2x times t, with v of x times t, the first correction involves that. And that's about a t squared. Okay? So, if we're only keeping terms to order delta t, we can ignore the fact that these two operators will converge. Okay? So you can write it as a product of two different operators. So that's what we're going to do. We're going to write this as follows, and you can write